Today we're going to look at some inverse relations and inverse functions. And the first thing we're going to look at is an inverse relation, so considering maybe a set of ordered pairs. And if we have an ordered pair, we'll just say for instance A comma B, and it's a relation if and only if that opposite, notice the switch, B comma A is in the inverse relation. So we're looking for the switch of the coordinates from AB to BA. So it says what's the inverse of the relation? So if we were to find the inverse of the relation, I'd want to take a look at the coordinates and think switch the coordinate order. So instead of 1, 2, I would have 2, 1. Okay, same thing for the next one. Instead of -4, 0, I would have 0, -4. Same thing with the last one. Instead of 6, -3, I'd have -3, 6. So that whole idea of inverse, switching the x and y, or switching the order, we want to kind of keep in mind. Looking at a test that we can do. Now, we've done the vertical line test before, and the vertical line test was to see if we had a function. Now we're going to get something called the horizontal line test, which will show this time more with the inverse. So it says the inverse of a relation is a function if and only if each horizontal line intersects the graph of the original relation in at most 1 point. So that's huge. So if we were to simplify it, the idea here is if I have a function and I draw in horizontal lines and the horizontal line touches the graph at only one location, then I can look at that function and say the inverse will also be a function. So if we look at some examples below, it says which of the graphs are graphs of. So for the first one, I'm trying to consider, is this a graph of a function? That's our first question. Meaning, does it pass the vertical line test? So maybe let's do that first. Looking at this first graph, I can see, yes, it will pass the vertical line test no matter where I draw a vertical line. It will only intersect the function at one location. So I can say, yes, that would be a function. If I look at the second picture, this is going to fail your vertical line test. Anywhere I draw a vertical line, I can see I'm going to hit 2 locations. Only place it won't hit 2 locations is right at the end of the graph, but as long as it fails at 1 point, I can say it's not a function. If I look at the graph below, again, drawing vertical lines, this one's okay. No matter where I draw a vertical line, it will only ever touch the function at 1 location. So this one I can consider also a function. Second question, it says relations that have inverses that are functions. So now we're trying to consider the horizontal line test. So if we were to draw horizontal lines, the question is, will I ever touch it at more than 1 location? Now we have to be careful because while maybe right here this looks like it's going to happen, keep in mind this is that parent function, that's that 1 over x function. And these are asymptotic to that line. Y equals 0, we can think our x-axis. So this will be okay. This will pass your horizontal line test. So I can say, yes, not only is this a function, but the inverse will also be a function. It passes both tests. That makes this function special. I can call this a 1-to-1 function because it passes both the vertical and the horizontal line. Our second example, again, it is going to fail that horizontal line test because I can see multiple locations that when I draw horizontal lines, it will intersect that function at more than 1 spot. So not only is it not a function, but its inverse will not be a function. And then if we look at our last graph, this was a function to begin with. This passed the vertical line test, but you're going to notice it's going to fail the horizontal line test. All right, so I can see all those places where it's going to hit more than once. So what that means is if I were to take the inverse of this function, I could say the inverse is not a function. Okay. So if we look at maybe some of the algebra connected to this, how do we find an inverse function? What is it going to look like? So This is giving us a little bit of technical info. You're going to notice again some of the key components of this definition as you're seeing it showing this switch. It's saying if I have a function, notice I have f of a is equal to b. Now the inverse, I have f of b is equal to a. Again, it's showing you that switch. So the x and y is getting switched. That's one thing you want to keep in mind when you're trying to solve. So if we're going to find an equation for this notation right there is meaning the inverse. We want to find an equation for the inverse function, and it's giving us a function to begin with. So the first thing I would do, maybe to get us a little bit more comfortable, f of x, why don't we make that y, okay? And looking at the function y is equal to x plus 1. So algebraically, if I wanted to solve for this, I want to think switch the x and y. So I'm going to rewrite this equation, but this time what I'm going to do is anywhere I see a y, I'm going to make it an x. And anywhere I see an x, I'm going to make it a y. Okay, at this point, the key thing here that you want to say to yourself is solve for y. So if I were to write down steps, maybe what I would say is 1, switch the x and y, and then 2, I want to think solve for y. So that's something we want to keep in mind here. Switch the x and y, then solve for y. So if I were to try and solve for y, I want to think, all right, well, we're going to either multiply each side by y plus 1 or think of it as cross multiplying. Okay, so I would have something now that looks like x, and I'm going to write this all out because this is a common place to make mistakes. And I'm going to set that equal to y. Okay, goal is to get y by itself. So in order to do that, first thing I need to do is distribute through. So we have xy plus x is equal to y. Now again, I want to get y by itself. So I want to think gather my y's on one side. Anything that has a y is going to go to one side. If it doesn't have a y, it's going to go to the other. So I'm going to move the y to this side, and I'm going to move the x to this side. Could I go in the opposite order? Sure. And that's absolutely no problem. Okay, so I'm going to move the y over. That means we're going to have xy minus y. That's how we're going to bring the y over. And then on the other side, I'm going to have equals negative x. Okay, so my y's are gathered. Now again, I want to think, get y by itself. So since each of these terms on the left-hand side have a y, I could factor out a y. So my factor that I would be left with here, so y times x would give me xy, y times negative 1 would give me negative y, and then I have a negative x on this side. And again, we're solving for y, getting y by itself, so now I can divide through. And now we can see over here our function y equals negative x over x minus 1. And keep in mind what that y is really like saying. This y here is really that f to the negative 1 of x, or your inverse. So our final answer is a negative x over x minus 1. That is your inverse function. Okay. We want to connect this with domain and range. So it says using the function x squared, what is its domain, what is its range? Well, x squared is one of our 12 basic functions. X squared, if we just think about this from a graphical standpoint here, it's our parabola. So rough sketch, that's our x squared function. So our domain for this function, we can see negative infinity, positive infinity, no restrictions, no square roots we have to worry about, no fractions, so I don't have to worry about the denominator. The range on this function will go from 0 and including 0 up to infinity. Okay, so now we have to find the inverse of x squared. Okay, so if we think of our steps, switch the x and y, solve for y. So I'm going to switch the x and y, and now we're going to solve for y. So I have to think, to undo a square, we would square root each side. And when you square root, you want to keep in mind, really what you're getting here is both the positive and the negative square root of x. But this is going to give us a little bit of an issue. If we were to graph this out, what you would see is your positive square root of x is going to look something like this. But your negative square root of x, well, that's just a reflection over the x-axis. It's going to look something like this. And if I were to try and think, is this a function? Well, no, it's going to fail that vertical line test. So how do I make my inverse then actually become a function? Since I'm looking at this notation and it's saying what is the function, that inverse function? Well, now we get something where maybe if I restricted the domain, I could actually get this to be a function. In other words, if I only considered the top half of the function, this section right here, and I didn't consider the negative half, so keep in mind that's coming from the negative square root of x part, then what I would do by restricting my domain is I would actually produce an inverse that is a function. So if we look at this now, only considering that top part, the domain of the function is going from 0 to infinity. And again, if I go back up to that initial definition that we had at the top of the page, notice what it's saying. It says the inverse function of f is the function with domain R, meaning the range of the original is now the domain of the inverse, and vice versa. The range of the original is the domain of the inverse, and domain and range are going to switch. Okay, so why did that not happen here? Well, if it did happen, we could see how we wouldn't get a function. If we restrict it, well, now we're going to get a function. So I have to restrict the original domain. Notice that the domain here is the range here. We're switching them. I could not make the domain of my original function be the range of my inverse because we came up to this graphical issue. So what we do is we say, well, let's restrict the domain of that function and only consider the positive section. So really the domain of the original function, I'm only considering from here over. And when I do the inverse, then I'm only going to get this top half. So on the bottom here, just a little side note, maybe to simplify it. The domain of the original function is the range of the inverse, and the range of the original function is the domain of the inverse. And we may have to restrict the domain of the original. Keep in mind, just so that we get the inverse to actually be a function. We'll see this come up with our trig functions as well once we get into those. Okay, and then the last thing, a way to tell if a function is an inverse. If they're inverses of each other, it's this inverse composition rule, saying that if I compose two functions together and I get out a value of x for each composition, that is going to tell me that yes, in fact, those two functions are inverse functions of each other. So we're going to try this, showing algebraically that f of x and g of x are inverse functions. In order for this to work, we have to do the compositions. So what this is saying here is in the f function, anywhere I see an x, I am replacing it with my g function, or the cube root of x minus 1. So in the f function, I have my x value immediately, so I have the cube root of x minus 1, and we're going to cube that, plus 1. So if we simplify, if I cube a cube root, those are going to reduce out, and I'm left with x minus 1, and I still have the plus 1. And nicely, this is going to simplify down to x. So right now I can see when I compose the f of g of x, I get x. But we have to show the other way as well. So I need to show the g of the f of x is also equal to x. So we start with the g function, and anywhere I see an x in the g function, I replace it with f of x, or I replace it with x cubed plus 1. So I have my cube root of x, And in place of that x, I'm going to write x cubed plus 1. And then we have a minus 1. Okay, well, working underneath the cube root to simplify, I can see we have the cube root of x cubed plus 1 minus 1 once I drop the parentheses. And that should leave me with the cube root of, well, plus 1 minus 1, that's 0, so the cube root of x cubed, and the cube root of x cubed is x. So what we have just shown now is that the g of the f of x is equal to x. And we've shown that f of g of x is equal to x. And so that means the original functions f and g of x are actually inverse functions of each other. Hope that helped. Please let me know if you have any questions.